Welcome to part 7 of this playlist about the preparation of pyridines. In this video we'll have a look at the nucleophilic amination and hydroxylation of pyridines by substitution of hydrogen. These reactions offer an inexpensive access to aminopyridines and pyridones, which are important synthetic intermediates. I will not discuss aromatic nucleophilic substitutions, for instance the conversion of halopyridines into aminopyridines, but I'll show you one example of the diazotation of two aminopyridines followed by hydrolysis to pyridones. Such substitutions are often easy to perform if the leaving group is at positions 2 or 4, but are not unique to pyridines. The most famous amination is the Chichibabin reaction. Treatment of pyridine with a sodium amide causes nucleophilic amination at position 2, followed by hydride migration and aromatization. After hydrolysis, 2-aminopyridine is obtained in good yield. Apart from the spelling of its name, this is otherwise an easy reaction. It proceeds best in apolar solvents such as xylene and often requires high temperatures. Instead of sodium amide, also deprotonated alkyl amines can be used as nucleophiles. With sodium or potassium hydroxide, however, much higher reaction temperatures are required and conversion and yields tend to be low. Let's check some specific examples. Best results are usually obtained with pyridines that do not contain any leaving group or acidic functional group. Sometimes, however, even 2 or 4 alkyl pyridines can be aminated with sodium amide, despite the high acidity of these alkyl groups. Here, for instance, a yield of 51% could be achieved by heating a mixture of 4-propylpyridine and sodium amide in toluene to 140 degrees Celsius for 2 days. It was also found that catalytic amounts of ethanolamine enhanced the rate of these reactions. Here, amination of 3-picoline with sodium amide was conducted in an autoclave in toluene at 150 degrees Celsius, and after about 2 hours a good yield of 2 isomeric aminopicolines resulted. If hydroxylamine instead of ammonia is used as nucleophile, no hydrogen but water will be eliminated during aromatization. Such reactions usually proceed more readily and under milder conditions than the standard amination with sodium amide. In this example, a highly reactive nitropyridine was aminated with hydroxylamine under alkaline conditions. The reaction already proceeded at room temperature. Simple, unactivated pyridines will not be aminated under these conditions, though. Stabilization of a negative charge by the nitro group greatly lowered the energy of the first transition state and thus strongly accelerated the amination in this instance. This is a beautiful example of the amination of 3-picoline with butylamine. The sodium amide was first prepared by refluxing a mixture of sodium, butylamine and 8% of 4-picoline as catalyst for 6 hours. Amination of 3-picoline by this amide only required 2 additional hours at reflux temperature and gave a good yield of mostly 1 isomer. The reaction temperature could be lowered even further to the boiling point of THF by adding an excess of lithium iodide. Its function probably was to act as a mild Lewis acid and to enhance the solubility of sodium hydride and of the sodium amide. Nitropyridines can be aminated with alkyl amines directly in the presence of some oxidant. In this example, a huge excess of isopropylamine and 2 equivalents of potassium permanganate brought about the clean amination of 3-nitropyridine. The scope of amines was limited by their sensitivity toward oxidation, and with benzylamine, for instance, the reaction did not work. Permanganate was probably reduced too quickly by this amine. One interesting alternative to nucleophilic aminations is the oxidative coupling of pyridine with 4-aminopyridine mediated by phosphorus trichloride. This reagent probably converts pyridines into pyridinium salts, but may also convert the aminopyridine of this example into an aminophosphine. Ultimately, phosphorus trichloride must act as an oxidant and be reduced to some phosphorus species of a lower oxidation state. Unfortunately, the scope of this strategy seems to be limited because I could not find any other examples than this one. Pyridines with halogens or other leaving groups at positions 2 or 4 will usually undergo a clean aromatic nucleophilic substitution when treated with amines. 3 halopyridines are less predictable though. As with haloarenes, elimination of the hydrogen halide might occur, and the amine can then add to any of the 2 sides of the triple bond, preferentially to the sterically more accessible position. In this example, the main product was formed by this elimination-addition mechanism without any displacement or cleavage of the ethoxy group. In the second reaction, however, a product mixture resulted from elimination-addition, reduction and chichibabin amination. Such results cannot be predicted and must be determined empirically. I'll show you now some examples of pyridine hydroxylations. Here, a highly electrophilic nitropyridine was treated with hydrogen peroxide and potassium terzbutoxide in liquid ammonia. Despite the availability of chlorine in position 2, addition to position 6 was faster. Elimination of terzbutoxide then yielded the final pyridone. 2-pyridone can be hydroxylated by treatment with persulfate, as shown here. The workup and purification of the main product was tedious and difficult, but the reaction was inexpensive and may still be a competitive approach to 2,5-dihydroxypyridine. Another way to hydroxylate pyridines is by oxidation of boronic acids or their esters. These can be prepared from methylated pyridines and trimethylborate, as shown here. In parts 2 and 5 of this video playlist, you can find many examples of the methylation of pyridines. The oxidation of boranes or boronates proceeds by addition of hydrogen peroxide or a per-acid to boron, followed by intramolecular migration of carbon to oxygen. Unfortunately, the direct oxidative hydroxylation of pyridines with sodium or potassium hydroxide does not proceed as cleanly as the chichibabin reaction. With quinoline at 225 degrees Celsius, the hydroxylation proceeded well enough, but pyridine, which is less reactive than quinoline, required a higher temperature. Copper catalysis seems to help a bit, but you will still need a Bunsen burner to get this hydroxylation to work. A much better strategy for the preparation of 2-pyridones is treatment of pyridine N oxides with acetic anhydride, followed by hydrolysis. This reaction is discussed in part 8 of this video playlist. Anyway, reaction of pyridines with sodium hydroxide would be less expensive, and a better catalyst for this transformation could be of value. Alternatively, 2 or 4 aminopyridines can be converted into pyridones by diacetation, as shown here. Because nucleophilic substitutions at positions 2 and 4 in pyridines are fast, the diazonium salts cannot usually be isolated and will be immediately hydrolyzed. Here are a few more examples that I've also listed in the description of this video. The next video of this playlist is about the preparation and chemistry of pyridine N oxides. These are quite easy to prepare from pyridines and can also be reduced again to the parent pyridine. Pyridine N oxides are more electron-rich than pyridines, and a number of electrophilic hydrogen substitutions proceed more readily with pyridine N oxides. These compounds also undergo some rather unique transformations. So don't miss part 8.